Всем привет.
Well,
Меня зовут
hi
Арсений Краснов. Я
everyone.
работаю
I'm
в
Arseniy
Sberdevices.
Krasnov. I work
Занимаюсь
in
всякими
SP
системными вещами, вроде
devices. I
ядра
work
Linux,
with different system things,
занимаюсь
and
контрибьютом,
well, I deal
ядро Linux
with
и так далее.
contribute
И сегодня
Linux
мой
and so on
рассказ
and so
будет
forth. And
про
today I'm going to tell you
пересечение
about
Wi-Fi и
intersection
Linux.
of
Ну,
Wi-Fi
Linux в
and
целом, не только ядра.
Linux in general, not only the kernel.
Собственно, спецификация Wi-Fi, она очень
Well,
большая, мы все с ней знакомы.
Wi-Fi
Всю ее охватить
specification is
невозможно в рамках
huge.
одного
It's
выступления.
impossible to tell
Linux
you
тоже
everything
большой,
about it within
поэтому
one
будем рассмотреть
presentation.
именно
Linux is
такие
also
случаи для
big.
пересечения.
We shall look at the intersection only.
Wi-Fi и Linux у нас есть, в общем-то, везде.
Wi-Fi and Linux is everywhere today. Access points and routers at home, in the office, in public places. It's Android phones, not only Android phones, because the stack operates everywhere. Desktops, notebooks, USB devices, Wi-Fi transmission, reception. Well, as I said, Wi-Fi specification is huge, so we shall look at the very top for general understanding. I'll tell you about the general view of the stack, about the most popular mode of operation, STA, scanning, connection, roaming, and a few words about access points. Well, a few words to begin with. What are the modes of operation? Station, you know, when we connect to the access point, then monitor, when we want to capture packets by Wireshark. And there is ad hoc, point-to-point, when the devices talk to each other without access points. But today we're not going to look at monitor and ad hoc because they are not very often met and they are not supported in some devices. Ad hoc is everywhere, but monitor is not everywhere. So we'll look at the station and access point only. Sorry? The general view of the stack, data plane and control plane. Data plane is simple, similar to any network interfaces. We have sockets, we have network subsystem, and under it a Wi-Fi driver, which works as a network interface. It has callbacks for transmission, reception, and we can transmit packets and work with the radio environment. That's simple, but if we go to control plane 802.11, so you will see a lot of things, because first of all, it consists of user part and kernel part. User is on top, blue, kernel is green below. User components is Wi-Fi supplicant, you've heard about it. It usually works as a daemon, and it provides supports operation in the station mode. In user is Webpack-Li online interface, a utility which can talk to it through dbus and UDP, text instructions, scanning, connection, and so. And also we have the choice of network, dbus. Supplicant has an access point through dbus. In the same hostapd, a daemon in the user space which supports access points functionality. They are similar, they are together because it's the same open source project, and they share a lot of things, including encryption. It has its own command line interface, same as Webpack-Li supplicant. It's all one project. Read the BEF file, I'll tell you about it. We cannot deal without it. Then we have kernel part. In the kernel part, we have subsystem 802.11, a separate one. It's not a network subsystem in Linux with socket with TCP/IP. It's a separate entity. We can have a state machine Wi-Fi, depending on the type of the driver. You can have their connection disconnection, scanning, and in supplicant hostapd talk to it through the interface called netlink. Netlink, I'll tell you about it a bit. Why? Because maybe you've heard about it, but few people looked inside. And into 802.11 subsystem, we have the same driver, Wi-Fi driver. It's just a network driver for transmission and reception, plus 802.11 device, which provides its callback for connection, disconnection, scanning, stopping the scanning, and so on. Well, a few words about, about netlink. What is netlink? Well, you all know what is a system call that we use to talk to any entity, and this is a one-way communication. We send something and get a response. Of course, we can work asynchronously, but it can take some time and effort. There is a need for multicast, but it's difficult because it is not designed for that. And one more thing is hardcore-based arguments. When we have a binary structure, we have to do something about it. It's not very reliable. How can we solve the first two problems? If we think all this is already done in the network subsystem, when we work with the network packets, as far as one-way communication is concerned, we get one packet from the kernel, the socket reads it, and the same is back way. We send it to the socket, and it is transmitted. Everything is simple. As for multicasting, for example, we have two applications, X and Y. They open packet sockets, socket X, socket Y, and if we get a message to the kernel and the kernel knows that we need a multicasting, it will the network subsystems can transmit it to both parties. Each of them will get its own message. And the other way around, if we want to send a packet, it will go to the kernel, to the network, and the kernel will support the multicasting. User and kernel can talk through mini sockets, which support multicasting. Instead of what we have here, we have a socket, IF netlink. Bind will be for broadcasting. We can transmit data. We can also do some specific things, and close means closing. This mechanism in Linux kernel can provide routing, firewalling. 802.11 also uses all that as transport protocol. Netlink as transport protocol. 802.11 is not shown here. It's network generic. A set of netlink receivers who are dynamically managed. They support 802.11. As far as struct arguments, we decided to make it simple. We add metadata, and that's all. When we read or write a packet, you will have a header and the payload. The header is standardized. Data is also split into several blocks. Each argument is transmitted with its own subheader. subheaders are blue, and data is 1, 2, 3, 4, a string. And this is the length and the type indicated in the subheader. We all need it because 802.11 uses a lot of parameters. Instead of X, we can put any identifier, for example, a channel descriptor, and that will help us. Not only 802.11 works, that routing tables do the same. One more profit is you can use nested data here. So in the data block, you can have several data descriptors. For example, if scanning is required, if we scan all the access points around, you get such a packet, trigger scan as a main instruction, and data information about frequencies. And in that case, we have metadata, which help us forget about porting. Now, let's go back to Wi-Fi. STA, station, the most popular mode of operation. We have a customer, the station, STA. For example, this is a phone connected to access points with a certain SID, SID, identifier, and the access point is connected to the internet, a typical case. In order to connect to the point, we need scanning. We need to scan the environment. Each access point transmits information about itself on a certain frequency. It's broadcasting, it's not encrypted. You can see it anytime. The interval can be any, but usually it's 1/10 of a second. It's SID, parameters of security, some other features which the access point supports. How does it work in Linux? If we want to scan the environment and then to connect, scanning is called passive scanning. Passive scanning is collection of packets. Supplicant says start scanning. We have such a request. We go to 802.11 subsystem, then the Linux kernel goes to Wi-Fi driver, and the driver should go through all the frequencies, get the beacons, and then asynchronously provide it back, like DevOps who collects something. Here we collect packet. There is one interesting point. Scanning is expensive, an expensive operation, because there is an incoming traffic and outgoing traffic. We have to collect beacons. Traffic goes in, comes in, goes out. So the workload on the chip is high, and performance can go back by 5 to 10 times, especially if there are a lot of access points around. And then, what about connection? We have a phone. It's a network stack. Supplicant says 802.11 connect. The subsystem goes to the driver. It's a classical handshake. 802.11 authentication request, access point response, then association request and association response. A classical handshake. No encryption. It's just a connection. In order to disconnect, we also make such request and get a response. After that, we get a response that we are disconnected. Encryption. How does it work? Encryption is very important. Today, we cannot live without it. There are some exceptional cases, of course, because in the previous slide where I spoke about handshake, traffic is not encrypted by default. We're not talking about web encryption because it's obsolete. WPA 2, 3, in that handshake, there is nothing about encryption. Encryption is different. First of all, encryption takes place in the chip. It's hardware encryption. You wouldn't see it in, well, the driver gets decrypted traffic. There are two types of keys. A key between the access point and the customer, and the group key, which is used by access point to interact with all customers connected to that point. So we have web, WEP, for web privacy. It's an old mechanism, it's not used, it's very vulnerable because the key size is very small and you can easily disclose it by brute force. WPA has larger keys, and EAP, the authorization mechanism, is used in Linux very often. EAP, Extensible Authentication Protocol, is a big thing. It's used to protect connection. You can read about it, it's standard. There are different things there, lightweight, EAP, PSK, pre-shared key, which is often used, EAP TLS, but we are going to speak about PSK.
Собственно, весь EAP организован в Linux.
EAP is organized in the user space in supplicant and for APD.
Но для примера, как это работает.
As an example, we have passphrase. It's a password that we enter when we connect to the access point. With key derivation function in Linux is PDK2, which goes in and we generate PAW's master key, PMK. It's already existing in the access point. At the user side, it's generated at the attempt of connection. It generates a random number, S.
Дальше точка доступа передает это число.
Then access point sends number A to the customer, and the customer has SA and PMK with pseudo-random function. In Linux, it's SHA-31512. It generates the key for unicast connection to that access point. Inside PMK, it's not just a key that we add. It's split into several parts, but it's a wide subject, and I didn't show it here. There is a key inside, which is used for the access point, and a key which is for group encryption, for generation of integrity code. So a unicast key to connect to the access point. So everything is generated. The access point does the same because we transmitted S. Then access point sends MGTK, a group key. It generates it itself and encrypts it through PTK and sends it to us. After that, we say we're ready and we can use the keys. What about transport? There is interesting things. EAP is away from 802.11. We use EAP over LAN, local area network, EAPOL, Ethernet packets in local network. We have an Ethernet frame, which you all know. We have destination, source, MAC addresses, and PIP. 802 8E, EAPOL. Then data, EAP data, and control sum. Classical Ethernet frame. Here, it's a packet. In order to work with it, we open the packet socket with appropriate protocol, 808, and gets EAP packets. It will filter it by MAC address, and then through read-write instructions, you can get such packets and generate keys. Supplicant and access point work in the same way here. In Linux, EAP supplicant and host work in the same way. They generate keys. They have an EAP machine. You can go and see. Under it, EAPOL for transport. When through packet socket, you get packets. You open the packet, you get data, we generate key as a result. When the key is generated, there is an EAPOL machine. It says to supplicant or host machine, here are the keys. They send them through netlink to 802.11. 802.11 goes to the driver, and the driver, by a vendor-specific method, enters the key to the packets. And now you can work in an encrypted way. That's the way it works everywhere. There is such thing as roaming, which few people think about, but we have it. What is it? Roaming means that you go somewhere. For example, we're connected to the access point with our MAC address. There is another access point. We work with it, and then we go away. We move across the office where the distance becomes between us and the access point become larger and larger, and we see that the other signal is stronger, and we have to switch to another access point. How? We need roaming to quickly connect between different access points with one seed. And another area is when we are connected to an access point, and there are two persons who come in with two notebooks, and they connect to the same access point, and traffic is huge, and there is another access point nearby. There is no traffic there, and we'd rather connect to that access point to unload the first one. Roaming provides optimal quality of signal for stations, optimal throughput of the network, and connection or reconnection should be as fast as possible. Roaming in Linux and 802.11 can be done. It is supported in 802.11. It's supported. There is a K specification which reduces the reconnection time. Scanning is a very expensive procedure. If you are in the office, it would be a catastrophe. There are a lot of access points. So we did the following. We know type of action packet, 802.11 is special service packets for different purposes. They are connected to connection and disconnection. The idea is for us to offload scanning. And all access points can scan the environment themselves and keep information about adjacent access points inside. If we start moving away from our access points, then our phone will see that the signal power goes down. It may send the request, and the access point will send back information about other networks. We shouldn't scan anything. We already have all the information. We have to choose one station and connect to it. In Linux, it's also quite simple. It can be done by the driver itself. It can just have neighbor request and get response with a list of access point and keep it inside. Then, after some time, when we ask it to scan, instead of scanning, heavy scanning, it will just give us what was received from access points. And we have fresh list of access points around. It's very good. It accelerates everything. It offloads us. The driver can do it. It sends a request, gets a response, and it can be done quite easily at the driver level. We send the packet, get a response, and keep the response in memory. There is a more interesting type of roaming to choose the optimal access point. It's a recommendation. It's a specification 802.11v. It's supported in Linux as well. For example, you are connected to a certain access point. Those two persons with notebook come in, connect, and start transmitting heavy traffic, video streaming with high quality, and we don't have enough throughput. And the access point can recommend us to connect to another access point X. All of them, all the access point exchange data about workload, and there is, if the access point believes that it's overloaded, it can recommend us to connect to another one. It's a pure recommendation. You are not forced to reconnect. 802.11 roaming, well, the decision is to be taken by the customer. No one is forced. In Linux, it works in the following way. We have three access points, A, B, and C. We are connected to A. A, B, and C know information about each other. A show us an action frame with recommendation. It goes to 802.11 subsystem, that it goes to supplicant. The supplicant has a special option, VNN, which supports this functionality, and supplicant can analyze the situation by a special algorithm and take a decision whether to connect to another access point or not. There is the third type of roaming, the most interesting one and unusual one it is used for the fastest possible reconnection. 802.11k and v. Disconnection and connection takes some time. It's not instant. Handshake is fast, but generation of keys takes some time. So connection is not instant. It may take several seconds. We disconnect and then we ask for connection, and there is no guarantee that the next access point will connect to you, so you are without internet for a few seconds, for some time. Now it looks like that. We're connected to A, we want to connect to B, we have to disconnect from A and connect to B. It takes time, disconnection and connection. We have to generate keys. It takes even more time. In principle, we can live like that. If we are in Messenger, if we read news, it's all right.
No, actually, I would just media. You wouldn't be bothered by these reconnects. However, if you're on a video call or you're using live voice, such reassociations will cause a lag that will cause disruptions. And 802.11r was designed to prevent this. Let's say you are associated with B, you have A and C as well. PMK goes around the network. They have their own A and C. So the device wants to reconnect to C on its own. It sends a fast transition request. It's a specialized Wi-Fi frame that asks for a fast switchover. APC considers this, generates a key in the background, it has the key ready, it gives an FT response, approving the reassociation. The device generates a key to interact with the access point C, sends a fast association request, get a response, to switch over, decouple from B quickly, and associate with C. You install new keys, and that's the entire procedure. So the switchover time is in fractions of a second. It's really great, but it's not universally supported. Its implementation in Linux is quite intricate. You need WPA supplicant and host that supports it, a lot of code. Then the driver needs to support the packets for FT as well. The supplicant can say that it's ready to switch over. FT request is sent, it goes to the driver. Then the driver needs to have the logic implemented in it for this. It'll take some time to do the keys. And then we'll get a response to the supplicant. It's not well laid out in the slides, but the procedure takes a lot of code, even if it's very much desired in terms of network usability. Last but not least, let's speak about access points in Linux. The daemon is hostapd. It's pretty much the same as WPA supplicant. Hostapd has a conf, subsystem 801.11. Netlink calls will be just a little bit different. Enable, disable the AP, and so on. Here is an example. You have the config, network interface, LAN 0, the driver is netlink, then SSID, STP that you see when scanned, channel number, and passphrase is password. It's pretty user-friendly. That's all you need to set up an access point. It just needs to be supported by the Wi-Fi adapter because cheaper ones may not have it. That's pretty much it, except for regdb. There is a catch. You cannot broadcast in all frequencies across different countries. Some countries may have certain bandwidths restricted. You have this in Russia, in the US, and Europe. Most of Wi-Fi frequencies are allowed, but there can be minor challenges. Some countries require a license to broadcast to specific frequencies. Sometimes they're classified as indoor and outdoor. There are frequencies that are occupied by weather forecasting, public alerts, the military. So that's why you have regdb. It's a frequency database for each given country. It has 2 character codes for countries and a table of allowed or restricted frequencies, including the split into indoor and outdoor. It's schematic. It's not how the table actually looks, so it's not real data, just a demonstration. When hostapd sets up an access point, it goes to the kernel, it calls regdb, and runs a check if that country allows the frequency. Hostapd communicates the code as well. Technically, you can broadcast in any frequency. You will not be rated for this. But if it's a big solution that you deploy on the city level or district level, you have to check the regdb. I guess that's it from me. A bit of an overview. I'll be taking your questions now. I see a hand. Thank you. Thank you for the presentation. I thought of a question. I looked into this as well, or something similar. Most Linux distros have proprietary software to work with Wi-Fi adapters, and documentation is not always available. So this layer between the adapter and the kernel is not well documented for Linux. Do you have examples of open source software to disassemble the stack? The driver is closed and proprietary. You have a lot of open source drivers in Linux, and chip firmware is usually closed. It has a sort of an OS. It lives within itself. This is usually off limits. In Debian and Gentoo, you have to constantly load it. Yeah, you can't do anything about it. It's closed. There is a driver for this chip, and that's it. Hopefully this answers the question. Yeah, sure, maybe you can use some examples. I guess there are open source developments, but most of these drivers are closed. Thank you. The standards have been evolving. Have they done anything to prevent DDoS attacks? Spamming SSIDs or sending thousands of transfer requests? Great question. What's been implemented to prevent such attacks? I didn't look into 802.11 in this regard, and I had to do this on my own within the driver. You can code something in C, 100 lines of code, that would generate a lot of garbage packets. And when you'll start scanning the air, you'll get a lot of FullMAC addresses and SSIDs. You'd have a lot of rubbish beacon packets. Your driver should better handle this. To your question specifically, I'm not aware, and in practice, I had to do this on my own. Your script, what if you specify the address for the target? Or what's the address of the target? So I ask the AP to connect to you. Yeah, why not? The packets are not encrypted. These packets are not encrypted. You just spoof the MAC address and go on with it. There are many attacks on Wi-Fi. It's been more technical in my presentation.
Спасибо большое за доклад.
Thank you very much for the presentation.
Девайсы интернета вещей таким же образом работают или там какие-то особенности?
Do IoT devices operate the same way, or are they different? Linux-based? Yes, then it's the same.
Спасибо.
Thank you. I see another hand.
Вот знаете, технология, когда
You know, there is this technology where there are many sensors in your apartment, And as you move, you transfer between access points, smaller access points, seamlessly. Is it there? What's the standard? 802.11? 802.11r is used for quick transfer switchover, but it needs to be specially enabled in your router. If you have several APs at home, you will not be doing this under any standard. You'll be always looking for a new access point. There is a logic for this in the supplicant without 802.11r or anything. It can be configured in the supplicant. Start scanning when the signal is weak. The driver will call the supplicant and you'll start scanning for a stronger AP with the SSID. So there is no specification for this. So it's not a separate implementation. You can just have many APs and do this. It's not a technology. If I have many Linux APs, I'll have this at home.
Да.
И дальше что?
Я могу это реализовать дома на Linux.
Да.
I'll have this with Linux. Okay, thank you.
И еще вопрос.
Another question. I wanted to ask about regDB. Is there a country where there are no regulations at all, or where everything is free for all? Everything is fair game. I'm not sure, I don't think so. I don't recall any entry where everything is allowed. There is a code in regDB. It's like RU for Russia, GB for Great Britain, US for USA, and there is 00 for the world. And you can do almost everything there. There aren't any regulations, but 2/3 of the frequencies are restricted there. So no, I don't recall any countries where everything is allowed. But set it to 00, the world, if you don't know what to do. You'll have a limited range, but it'll be legal for sure. A question? Can I? Sure. I came in later. Can you force disable DFS? I'm guessing yes, but I never checked.
Друзья, есть? Да, отлично.
Friends, one more question I see. Thank you for the presentation. My question is this. When you discussed roaming, you mentioned that you connect to Wi-Fi and then there is a bad actor who is loading the traffic and you get a packet to switch over to another network. Why do we get this packet, not the other user? It's implemented within the access point. The algorithm that's there will be what decides. And it's a recommendation. Maybe it won't. It depends on the vendor. So there is no priority to the client. No, I'm not aware. It's based on the load on the other access points. It's based on the types of clients. Okay, thank you.
Так, давайте последний вопрос. У нас...
Let's have one more question since we're running out of time.
Здравствуйте.
Hello. I recently purchased a Wi-Fi router, and it broadcast 5G and the regular Wi-Fi at the same time. It was there out of the box. I redid the firmware with OpenWAT. I wanted to do the same, but I couldn't find it. On the forums, they say that I should have 2 access points with the same name on the same router, 5G and the usual one. Is there a more elegant solution? And what are the potential attack vectors? As for the implementation, That's how it's usually done. These are two supplicants, or two host APDs rather, and they have two different modes of broadcast. In other implementation, well, under the hood, it used to be the same. It was just a pretty interface. So it's two networks, same name. Yes. Two physical access points that work in different ranges, 2.4 and 5. As for attack vectors, I'm not sure. I haven't encountered that. That's it from me. Thank you. Thank you as well. So, which question did you like the most? That one, about DDoS on Wi-Fi. Very pressing issue. Okay, round of applause. Thank you.